Hello and welcome to 1.2 Functions and Function Notation. This is a part 1 of 3 video series. Let's first look at our learning goals. These are going to be carried forward from our first lesson. So the first one is demonstrate an understanding of functions and their representations. Today we will be looking at some new representations. So our success criteria: determine if a relation is a function when the relation is represented as a table of values, mapping diagram, graph, function machine, or an equation by performing vertical line tests or identifying one-to-one or many-to-one mappings. Okay, this is our success criteria from our last lesson. However, we're going to be focusing on mapping diagrams and function machines. Okay, those are the two new ones that we'll be looking at in this lesson. We're also going to be using the one-to-one or many-to-one mappings to determine if uh, these relations are functions. And our next success criteria: represent and evaluate functions using function notation, given their equations, table of values, or graphs. Okay, so we're going to be learning how to take our functions and actually put them in the proper function notation. All right, let's begin. So we're going to first talk about function machines. So these machines will take an input value and generate an output value by performing a specific operation. So here we got a function machine, and we don't really know much about the function machine. We just know it takes some input and then comes up with an output. So let's see what happens when we take the number 1 and put it in. If we put 1 in, the 1 kind of enters into this machine here and does a bunch of mathematical operations to it, and when it comes out, it looks like a 5. Okay, and then 2 goes in, comes out as 11, and 3 goes in, and something happens to it, and it comes out as 14. Okay, if I were to tell you that this function machine has a linear property to it, or that it follows like a linear relationship, what do you think that equation would be, or that rule that it's following? Okay, so 1 goes in and it must be multiplied by something, and then maybe something is added to it and it becomes 5. That same rule applies to 2, and then it comes out as 11. And the 3 also multiplied by that same number, and then something added to it comes out as 14. Okay, I will give you a second to try to come up with that equation. You can pause the video, and when you return, you'll be able to see the answer. All right, so hopefully you might have guessed this. Y equals 3x plus 2. Okay, this looks like a linear equation. We can see here if 1 goes in for x, then 3 times 1 gives us 3 plus 2, and then we get our 5 out. Okay, so we can see how 1 turns into 5, and same with 2 turning into 11 and 3 to 14. All right, it's really easy to state our domain when it's in this form because our domain is just all the input and our range is just all the output. Okay, so the domain is the input and the range is the output. Okay, and remember we list them in set notation with the brace brackets. These should always be in ascending order when you list them, and we don't repeat any values. Okay, we could put this in a mapping diagram form, so we'll just get rid of the function machine, get rid of our domain and range here. We'll bring these a little bit closer together. Okay, and the next thing we do is we just draw directed line segments to show which input value maps over to the output value. So we can see here that 1 maps to 5. Notice there's a little arrowhead on the end here. 2 maps to 11, and 3 maps to 14. So it actually shows which input corresponds to which output. So these are called mapping diagrams. They're graphical representations that relate the values in one set, the domain, to the values in a second set, the range, using directed arrows from domain to range. So it always goes in that order, from domain to range. All right, let's do an example. Express the following order pairs in a mapping diagram. So now we're given the order pairs. It's kind of like having a function machine. We see the input and the output. Okay, we're gonna have to draw these inside an oval. Okay, so this will be our domain, and we're going to grab all the x values, 1, 2, 3, and 4. We're going to put them in ascending order from the top down. And then we'll grab our range, all the y values. Okay, when we grab these y values, don't repeat any that may be repeated, and put them in ascending order. Now for the fun part, the mapping part. 1 maps to 4, as you can see in the ordered pair. So 1 will map to 4. 2 must map to 3, and 3 goes to 6, and 4 goes to 8. It's okay that these mapping lines crisscross. That is allowed, okay? And you can see this really gives us a nice picture of the function. So is this a function? Okay, so in order to be a function, each input must only have one output, okay? Or each x must only have one y. Okay, so yes, this is a function because each input only points to one output. So this would be considered like a one-to-one mapping. Okay, one-to-one mapping. Each input points to one output. All right, let's look at another one. Okay, we got quite a few ordered pairs here. Okay, so let's go ahead and draw our domain. Now we're going to write all the numbers in ascending order. Be real careful. We're looking at all our x values. We have 3, 2, 1, 4, 5, 6, 5. So they kind of jump around a bit. Lowest is 1. Okay, so those will look like 1, 2, 3, 4, 5, 6. Okay. All right, now carefully grab the range. Okay, put those in ascending order. Smallest value is -5, and then we got -1, then 0, then 5, and 8. Okay, now the fun part, drawing our mappings. Okay, 1, I can see here from the ordered pair, 1 maps to -5. So I should see a nice line going straight across. Okay, 2 maps to -1. Okay, so far so good. And 3 maps to -5. It looks like this one's gonna have to cross over. And it does. Okay, 4 goes to 0. 5 goes to 0. 6 goes to 5. Oops, looks like those are backwards. 6 goes to 5. And lastly, 5 goes to 8. Okay. All right, now the big question. Is it a function, yes or no? Do we have one-to-one mappings here? Or do we have any two-to-one mappings? Or 1-to-2 mappings, I should say. Okay, so everything looks good except for the 5, right? Okay, so we're going to say no, this is not a function. Why? Because 5 maps to 0 and to 8. So it has a 1-to-2 mapping. We can see that right there. Okay, so that is mapping diagrams. It's just another way of representing relations. Okay. All right, now we're going to talk about expressing stuff as a function. Okay, function notation. This is how you're going to see functions kind of for the rest of your mathematical career. Okay, this is most of the time functions are expressed in this notation. Okay, so it's a new way to represent functions. To write a function using function notation, the form f of x equals something is used. Okay, so we no longer use that nice y variable. We get to use this f of x instead. Okay, so for example, the previous function machine followed the linear relationship y equals 3x plus 2. Okay, so if you guys remember from our first function machine, we had the equation y equals 3x plus 2. Well, if we were to write this as a function, we just replace the y with this new symbol f of x. And it would look like this. This is function notation. Okay, so we just switch y with f of x. Okay, so just to make sure we understand what to do when you see this, you don't have to freeze up. If you have to say this out loud in class, you just want to read it as f of x. That's what this f of x part. That's how it is read. Okay, so there are some advantages to this. You might be saying, Mr. A, why do we got to write it like this? It seems like a lot more work than just writing y. Well, the first advantage is that it actually lets us know the equation is a function. So it is kind of a good reason, because right away when you see f of x, you know that you're working with a function and it's going to follow the rule of each x having only one y value. Okay. It also helps us identify the independent and dependent variables. Okay. So x is the independent variable, and we call that the input, and f of x will be the dependent variable. This is our output, the y value. Okay, lastly, it makes it easy to evaluate functions when given a value for x. Okay, so an example of this would be if we were given that equation and we wanted to find f of 3, we would just substitute 3 in for x and then solve. So if this was our function, f of x equals 3x plus 2, we can evaluate f of 3 just by plugging 3 in for x. Okay. What's nice about this notation is when we see f of 3, like we have right here, this is telling me to evaluate the function when x is 3. So it's a quick, easy way of saying that. Okay, if we were to do this, it would look like this here. We would substitute 3 in for x. So if we look at the equation up here, we got to put 3 in for x. So that's what we've done here. And 3 times 3 is 9. 9 and 2 gives us 11. So it really, when we see evaluate the function, it just means substitute the value in for x and then calculate the value of the equation. Okay, let's practice some of these. So for example 3, for each function, determine f of negative 2. Okay, so here are a couple functions. Okay, so we have a linear, we have a quadratic, we have f of x equal to 11. We call this a constant because it's always 11. And then this one is rational, kind of an ugly looking equation here. All right, so we want to determine f of negative 2. So this means we just need to substitute x equal to negative 2 into the function. Okay, so we're going to take negative 2 and we're going to plug it in for x in each one of these. Okay, this will look like this here. There's our substitution of negative 2 in for x. So 2 times negative 2 becomes negative 4, and negative 4 minus 4 is negative 8. So I now know that f of negative 2 equals negative 8. Okay, let's do the next one. We're going to substitute negative 2 in for all the values of x here. Wherever you see them in the equation, you need to take the number that's in here and plug it in for x. So there is our substitution. We have 3 times negative 2 squared minus a negative 2, that's going to become a plus, and then plus 7. Okay, negative 2 squared is 4, so we have 3 times 4 plus 2, remember because there's 2 negatives, and then plus 7. So 12 and 2 and 7 give us 21, so the value of this function would be 21 when x is negative 2. Okay, this next one here, what are we going to do for this one? Okay, well, it's actually really easy. This function is equal to 11, always, no matter what. Okay, there's no variable term in here, so finding f of negative 2 is just going to be 11, because f of x always equals 11. Okay? This would be an example of a horizontal line, okay, like y equal to 11. Okay, where no matter for what value of x, y is always 11. Okay, let's look at this next one here. Okay, and that just kind of all came up at once, but we can see here we've just substituted negative 2 into the function for x. Okay, we replaced x with negative 2. 2 times negative 2 is negative 4. Negative 2 squared is positive 4. Okay, 4 minus 3 is 1. So negative 4 over 1 is just negative 4.